toy example to understand how the multi-layered perceptron works. Say you have two inputs and the output is 2-class problem. And here, if you see, we have two hidden layers. One hidden layer has 3 neurons, another hidden layer has 2 neurons. And you have the output. Okay. And for now, discounting bias. For now, the bias which we are going to have, right, usually this we are going to ignore. So one is a bias. This bias I'm going to discount now. Okay. How are the weights assigned? Randomly. Okay, so the weights are randomly assigned. So you say this weight into this input plus this weight into this input. And then if you pass it to your integration, you have this. Then when you pass it to your activation function, you get the output, which is y1. Then this input, this weight into this input, this weight into this input. When you do that, you get the integration function. Then you pass it on to the activation function. When you pass it on to the activation function, you get a value which is y2. Then you take this weight into this input, this weight into this input, that would give you the integration value here. Then pass it on to the activation function, and then you get the output y3. And all the weights are randomly assigned. Now these values will go to the next layer. And weights are again randomly assigned. And then you'll have integration components. So you use this weight into this, plus this weight into this, plus this weight into this. That would give you the integration component. Pass that into the activation component and you get an output. Once again, do this. Take this weight into this, plus this weight into this, plus this weight into this. And that would give you your integration value. Pass on that integration into the activation function, and then you get the final output, y5. Then move forward, and then you get the weights. These weights are also randomly initialized. So this weight into this, plus this weight into this would give you the integration component. Take that integration component and pass it on to the activation component. And then you get your final output, which is the predicted value. Once you get the predicted value, what do? You compare it with the actual value. And when you subtract your predicted value and actual value, what do you get? Error. Now, this guy is the probably manager. Okay. This manager, when he has done a presentation, there were some errors. And the board of directors will say that I'll put a penalty on you. Your bonus will be deducted because you've done a mistake. Right? Then what will this manager do immediately? He'll go down to the team leads. You will say, my dear team leads, I'm going to deduct your salary, your bonus also. So the moment this manager goes back and says, hey, I want to deduct your salary, this team lead will say, do you know what? I only gave you Y4. I've only given this much. Another team lead is there. He has also given you some input. So don't just deduct my salary, deduct this person's salary also. So this manager will say, okay, how much did you give me? Weight W46. This much weight I've given you. So that much amount of error, take it as a penalty. For this guy also, for this team lead also, this team lead will say, I've given you W56. This is a weight that I've given. This much amount I've given. So that much amount of error, take it as a penalty. Now, will the team leads keep quiet? No. They'll be like, let me look at who are the team members who have given me the inputs. They'll go back. And they'll go to say this team member. This team member might say that I've given some inputs W24 to the team leader Y4, and I've given W25 to team leader Y5. So they'll say, okay, that much amount of penalty, take it from this team leader. This much amount of penalty, take it from team leader, this. And then overall you get delta 2. Then you have W34 into delta 4, W35 into delta 5, which is taken as a penalty for this team lead, and so on and so forth. Then ultimately, what is the formula to get the new weights? Old weights plus eta value into error into your input. Correct? And that is exactly what is being applied here. You're finding the derivative with respect to the errors. Okay? And then ultimately you get the new weights. And this process of getting the new weights will continue for all the hidden layer weights also. And finally you get another set of outputs, predicted values. Again, calculate the error, again do the same thing. Going back, first of all, traversing forward, then going back and updating the weights is called as backpropagation algorithm. And the idea is to update the weights to minimize the loss. Okay, let's discuss about network topology. You have your input layer, one hidden layer, and you have two neurons in your output layer. If you have more than one neuron in the output layer, you call it as multiple output nodes. Okay, you have multiple output nodes. You have your input layer, and you have two hidden layers. One hidden layer has 3 neurons, another hidden layer has 3 neurons, and then you have your output layer, which has a single neuron. So you can either have a single hidden layer or multiple hidden layers, right? Yeah. If you have a data set like this, wherein you have the input layer and output layer without hidden layers, what algorithm is this? Perceptron or multi-layered perceptron? Perceptron. This is perceptron algorithm. And when you have input and then if you have hidden layers, etc., then this is called as multi-layered perceptron. If every neuron is connected to every other neuron, then it's called as dense network or fully connected network. Perceptron handles linear boundaries. Multi-layered perceptron handles non-linear boundaries. How does multi-layered perceptron handle non-linear boundaries? By including activation functions which are non-linear in fashion. You don't use linear activation functions. You use ReLU, sigmoid, tanh, some other activation function which captures the non-linear pattern. Okay, there are a lot of libraries which one can use to accomplish the task. And we have torch, which was introduced to the world in 2002. Not many people are using this. We have Piano, not many people are using this. Cafe, also not many people. TensorFlow, yes, a lot of people are using TensorFlow. And today as we stand, this is called as low-level programming language, meaning you need thorough programming knowledge to be able to write code within TensorFlow or by making use of TensorFlow framework. Because it is very difficult to understand and learn and write the program, there was a guy by name Francois Chollet. He has come up with Keras. Keras is a high-level programming language. And from TensorFlow version 2 onwards, Keras is incorporated into TensorFlow so as to make the life of people very easy in terms of writing the code. And this TensorFlow is fast because it's low-level programming language. TensorFlow is from Google, by the way. And then today, as we stand, we have something called as PyTorch. We can say that Facebook is a kind of parent of this. They try to take Torch and combine with Python, and they call it as PyTorch. Today, as we stand, this is a number 1, and this TensorFlow Keras combination is number 2. Okay. These are various libraries. Okay. So Keras or TensorFlow, or for that case, PyTorch also can be used on CPUs, GPUs, and TPUs. Okay. All right. So there are far too many things within deep learning neural networks. But then there are a lot of challenges as well. While deep learning neural networks can handle very complex data, huge data, a lot of relationships, very complicated data when you have, certainly deep learning or neural networks will help you immensely. Okay. But then there are a lot of challenges, such as most of the loss functions are non-convex in parameters, means it will look like this. It's not like this. If it's like that, if the weights are initialized here, you know that there is only one minima. But here you'll have one minima, here, 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 anyways. And when it's random, when the weights are randomly initialized, you don't know where you're going to fall on this error surface. Second, you have different initializations. If the weights are initialized here, you'll go there. If the weights are initialized here, you go there. If the weights are initialized here, you'll go there. So you have different minimas where you might reach. And you'll have lack of interpretability. Here you'll have weights. Okay, all these will be weights. All those weights will have different meanings. Okay, not different meanings, sorry. You cannot give any meaningful information to those weights. For example, if it is some kind of linear regression, if you have data like that, and say output is mileage that you're trying to predict, and if you have 8.2 plus 1.3 into weight of the vehicle, something on those lines, right? So what is the meaning of 0.3? 0.3 here means if you increase the weight by 1 unit, weight will increase by 1.3 units. That's the meaning. If you increase weight by 1 unit, mileage will increase by 1.3. Ideally, it should have been minus. If you have minus, then if you increase the weight of the vehicle by 1 unit, 1 kilogram or 1 pound, mileage will reduce by 1.3. That is the interpretation that you are going to have. Whereas in neural network, so you're predicting mileage, and then you got some 0.6 minus 1.03 into weight. This value has no meaning. There is no interpretation there. Okay. And also, whatever your hidden layers are going to learn, what patterns your hidden layer is going to learn is unknown, black box. Okay. So you will not have interpretability. Ablation methods with various arguments, meaning if I ask you how many hidden layers should I have? Experiment. There is no concrete way. Okay. Number of neurons in the hidden layer? There is no concrete way to figure out. What activation functions will you use? You don't. There's no explainability. You cannot reproduce the results. Why we cannot reproduce the results? Because each time you run the algorithm, weights are randomly initialized. Since weights are randomly initialized, we don't know. We cannot get the same result. We have a lot of tools, libraries, frameworks, which we can make use of, however. And United States DARPA Defense Agency, right, is trying to work on explainable AI. And they're trying to make this come true. Let's see what they're going to do. Okay, fine. So let me download the Python code and the datasets. We'll run the code, then post lunch break, we'll get into CNN, then we'll get into RN. Okay, let's first continue this. Okay. Let me run this and see. Don't throw me error, please. Okay. So I think I cannot run it on my local computer, but nevertheless, take this and run it on the Google Colab. Since how long was that not coming? Just let me know, friends, because I don't turn around and see it. Okay. So when it comes to Google Colab, when you go to runtime and click on change runtime type, you'll have an option to choose GPU. Okay. Since I'm using the paid version, I also have the option to use a high RAM. You might not have that. And let me click on connect. So Google is now trying to allocate the right hardware. So I'll import the required libraries. TensorFlow, etc. would be pre-installed on Google Colab. Okay. So from TensorFlow Keras, what did I say? Keras is very much part of TensorFlow from version 2.0 onwards. You're going to layers and you're importing dense layers. Dense layers means every neuron will be connected to every other neuron. Then there are other libraries. We are importing sequential. Sequential means first you have input, then you connect it to hidden layer, then to the next hidden layer. In a sequential manner you do it. You're importing NumPy as NP. You're from Keras utilities taking some utilities. We'll see on how to where we are going to use those utilities. And I'm sure you're aware of setting the random seed. Then there are these two data sets, training and test samples. But the path has to be changed. So what I'll do is I'll click on this folder icon and I'll just click on upload. Go to training dataset and select these two, put it here. So you'll get it here. When you close this, those will be gone. So if you see here, these two are getting loaded here. Yep, we have these two, right? So I will click on the three dots over there, copy the path, and we are going to paste the path. Then I'll also go here, copy the path, and I'm going to paste it here. Sorry? Oh, I did not import it. Import pandas as PD. And then we read the file, training and test, and put it here. Then we have these lines of code. So what are we doing here? We are saying that go to the training data, take all the rows and columns from 1 until end, take all the values of that. Always, I insist on having proper spaces and all that. Okay. So let me open the training sample. So the first column here is a label. Label is either it is 0 or 1 or 2, all of that, right? Handwritten digits. And every handwritten digit in this specific data set, for example, if you have 0, it will have pixels, correct? And this specific data set has 28 by 28. 28 by 28 is the dimensions or pixels of the images in this data set. 28 by 28 multiplied by 28 will give you 784. So you'll have 784 columns. And the first column, 785 rather, 784 are the pixels. And one is whether the digit is 0 or 1 or 2, etc. would be there. Okay, label can be 1, or label can be 2 or 3 handwritten digits. Okay, it's a 10 class classification problem. So what are we doing? We are saying that take all the rows from columns from 1 until n, because index number 0, that's column, first column is a output variable. You're taking all the values and you're saying convert them into float. Why are we going to do that? Why do we do that now? Suppose you have a network like this. How are all these weights initialized? Randomly, correct? All these weights are randomly initialized. And when all of these weights are randomly initialized, You can also have decimal values like 0.86, 1.32. You can have decimal values. So the weights will be in float format, whereas your inputs are in integer format. Inputs might be in integer format. So what you're doing is you're ensuring that all these inputs also become float. So when you change your inputs as float and when your weights are float, when you multiply those, you get the output which will be float only. Hence, the only place, I mean, you cannot obviously say that weights should be integers. That you cannot do because that is how algorithm works. It will only generate random weights. The only thing that you can control is your inputs. So you're converting your inputs into float format. Your outputs also you're converting into float format. Then we are normalizing the data. Let me copy everything rather than run each line of code. Okay. So we know for a fact that pixel values range from 0 to 255 in an image. If image has pixels, pixel values range from 0 to 255. 0 means black color, 255 means white color. And if you divide all the values by 255, what happens? If you have the minimum value 0, if you divide it with 255, you get 0. And the maximum value is 255. And if you divide it by 255, what do you get? 1. Mm. Why do we normalize on day 1 itself? We have discussed. Okay, now, what is the next thing? We are taking our output variable and this NumPy utilities or Keras utilities that you have. You're taking those and you're converting your output variable into categorical. Categorical will convert your data into one-hot encoding. So if you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if you have a 9 class problem, for every row, it will say either it is 0 or 1 or 2. Now, what are you doing? You want that to be placed like this. And if the first entry is 0, you put a 1, rest all will be zeros. If this is 1, you put a 1 here and rest all will be zeros. Why do you want to do that? Is the question, right? Why are you converting your labels into one-hot encoding? The reason why you convert into one-hot encoding is because if you have a digit 1, what will be the actual values? Zero, 1, 2, 3, 4, 5, 6, 7, 8, and then save. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 1, so we put a 1 here. Rest all will be zeros. Okay, these are the actual values. And then you have predicted values. In predicted values, you'll have some numbers, prediction. The 0.1 probability that it is 0. Okay, 0.8% probability that it is 1. 0.01 probability that is 2. In that way, you'll have the values. Now, how do you calculate the cross entropy? Pi into log of Qi. To calculate the cross entropy, you need the actual data in one hot encoded format. Only then can you calculate this cross entropy, and that is the reason why you're converting your output variables into one hot encoding. And a short form or an easy way of converting your output variables into categorical is using this. NumPy utilities convert this into categorical. Now, when you run this, only this line, will this work? I'm not sure. Very good. Okay. When you say of 0, it will tell you that you have 1000 rows. Of 1 means 10, because it has 10 classes. 0, 1, 2, 3, 4 in that way, right? Those many columns. So that you're storing in number of classes. Then if you just say shape, it will say we have 1000 rows and 10 columns. Then for X also, you can look at the shape. Y, you can look at the shape of these. Obviously, if you say print, only then will it show you all the details. Okay, this is what you have. Okay, now we are designing the NLP. It's a 10 class problem. Why are we getting 6 here? The data not loaded properly. Yeah, it's a 10 class problem. That's what I was surprised. Something somewhere went wrong. Anyways, so you have 5000 rows, 784 columns when it comes to training data inputs. Training data output has 5000 rows and 10 columns. This is how it is. X underscore train will have how many rows? 5000. And how many columns do we have? 784. Because each image is of dimension how much? 28 by 28 means 784. Pixel 1, pixel 0, pixel 2, pixel 3, pixel 4. In that way, you have 784 pixels. And then in this, you have 10. So Y underscore training data has, again, how many rows? 5000 rows. And how many columns do we have? 10. Digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Test data has 1000 rows, 784 columns. Test data output has 1000 rows and 10 columns. This is the dimension of the data that we have. Next, you're defining your own function. You can give any name of your choice, open, close brackets, colon. The moment after colon, when you enter, you will have this indentation automatically created. You're saying, let me initialize a blank sequential model in which in the input dimension, I'm going to have 784 neurons. And then I'm going to connect to 150 neurons. What kind of connection you want to establish? Dense, meaning every neuron will be connected to every other neuron. And in the activation functions here, you're going to have ReLU activation function. To that, you're adding another dense network with 200 neurons. Activation function is tanh. It's your wish. You can use any activation function. Then we are adding another hidden layer with 100 neurons. Again, we are using tanh activation function. Then that is connected to number of classes. In number of classes, how much did we get? 10. It's a 10 class problem. This is where we looked at it. Number of classes. 10. So you take number of classes which happen to be 10. And then since it's a multi-class classification problem, the activation function should be softmax. After that, when you compile the model, you create your network. When you compile, you're using categorical cross improvement. And metric, which is used to monitor your model evaluation, would be accuracy. If you have more than 2 categories, what do you use? Categorical cross entropy. And what do you use? Softmax. Metric being used is accuracy. So you define your model. And you're storing that in something called as model. Now, when you say model.fit, okay, run the model using my inputs and output, batch size will be 1000. When I say batch size equal to 1000, would it run batch gradient descent? Or would it run stochastic gradient descent? Or will it run mini batch SGD? Mini batch SGD, obviously. Since we are saying, yes, good. A lot of you all are able to focus. That's a good part. Only when you say dot fit, it's going to run the algorithm. In this model, you'll have all these hyperparameters defined. How many neurons do I need to have? How many hidden layers do we need to have? What activation function do we need to have? All this is defined here. And you want to run 10 epochs. Run it. And once you finish running the model, you can look at the summary of the model. So epochs will be running. Now, oh wow, good. It was so fast, yeah. It took 4 milliseconds per epoch. Because it's a GPU machine. On CPU, if you run, it will be very easy. Accuracy was very less when it initially initialized. Slowly and steadily, accuracy kept on increasing. And the loss value was very high initially. Loss value was high, and then it kept on reducing. And it reached the minimum. If you run more epochs, probably it will further decrease. And when you look at model summary, in the initial layer, we had 784 neurons. Then we added 150. Then what, 200? Then 100, right? Then you have 10 neurons. So 784 plus 1 bias will be there. So total will be 785 into 150. Those many connections will be there. So that is what you get. Okay, and so on and so forth. So here again, you look at the multiplication to see how many neurons you're going to learn. Okay. In total, how many parameters are we going to have? 169,060 weights, different weights will be there. Now that you have built your model, you are going to evaluate your model on the test data. When you say model.evaluate, give the test data input and output. It will score the model. It will store the model here. And when I say verbose equal to 0, for example, it will not show you any output. Let me do one thing. Let me copy this entire thing. And now I'll play around with this. If I say verbose equal to 0, it just gives you the loss and accuracy. When I say verbose equal to 1, it will show you the progress bar also, how much time it has taken. And verbose equal to 2 would give you some other information on how many milliseconds it has taken for this epoch, for this step, how many milliseconds did it take in that way, right? So that's what verbose does. Verbose equal to 0 means it won't do anything. Now, what you're saying is store the results in this, both accuracy and loss values. And loss will have an index number 0, accuracy will have an index number 1. So you're saying go to this 1. You're storing in this both 0 and 1. Take 1 and multiply it with 100 so that this is represented in percentage terms. And I want only 3 decimal values. Okay. Same is the case with training data also. Evaluate your model on the training data. You will store the loss and accuracy here. Take the accuracy and then you get the accuracy percentage. So your test accuracy happens to be 89% and training accuracy happens to be 91%. All right. So we just concluded the ANN part or MLP, artificial neural network or MLP. Next, we need to get into convolution neural network. But before we get into CNN, we will break for lunch. What is the time now? It's 12:35. Can we be back by 1:35, 1 hour break? Let us take 1 hour break, come back. And at 1:35, we will start with CNN. We'll complete CNN. Let's see how much time it's going to take. If we have time, we will get into RNN also. Take a break and come back to this. Thank you.